Hello, and welcome to Variational Inference Part 4. Um, my name is Chieh from Northeastern University. So today, we are finally going to go over the derivation. Unfortunately, I don't think we'll be able to finish the entire derivation today in today's video, but probably in the next one. Now, while we're going over the derivation, I highly recommend that you copy down everything I'm saying and try to follow it step by step yourself. So to make sure that you can actually do each step. That way you can learn the material as I go along. I mean, this is a video, so you can pause it and I'll just wait for you. So that's what you want to do. It will be very useful if you can step through the whole thing. And if you can follow, it means that you will truly understand what I'm doing. So let's start for today. Let's say that there are two sets of variables, x and z. I pick z as actually a set of 3. I mean, it could have been 4, 5, 6, 7. It doesn't matter. Similarly with x, I picked 3 as well. It could have been 2. Again, it doesn't really matter how many. I just happen to pick 3 variables randomly for each one of them. But I got to pick some number to demonstrate the idea. So anyways, they have a joint PDF of this, right? Because there are 6 variables. Of course, I'm kind of lazy, so I don't want to write all of them down. So I shorthand it. So this is the short version, but it means the same thing. Again, now we want to find the conditional, something like conditional probability of z given x. Again, I want to remind you that the longhand for this means this, okay? Remember, probability of a conditional is the same as joint divided by the marginal. Now, if I want to find the conditional, I take the joint and divide by the marginal. Most of the time, as we have talked about in the last class, the joint is provided. It's pretty easy to get. Not a problem. However, then you got to solve this integral. And this integral might not be very friendly to you. If it's easy, yeah, you just solve the integral and the problem solved. But here's the big but. What if the integral is really hard? Like really, really hard. It's so hard, it's impossible. Right? You have a really hard integral. What do you do then? Well, you want to somehow go from the joint to the conditional. And that's where your variational inference comes into the picture. Now we want to know, like I want to restate the problem because I want to bang this into your head. That here's the, we want to know the conditional. And we already know the joint. So what we do is we use Q of Z123 to estimate this. So I will use this to estimate the conditional. So the goal is therefore to find this for the estimation, and we want this to be as close to the conditional as possible. Okay? I repeat, we're trying to use the Q of Z to estimate this. And ideally, they will be as close as possible. Now remember, when we're estimating the conditional using Q of Z from other videos, we use this relationship with the lower bound, KL divergence, and log of P of X. Well, when we do that, we decided from the previous videos that when we want to reduce the KL divergence, it's the same as increasing the lower bound. So if we find a maximum lower bound, that's the same as finding the best KL divergence. So, well, here's the equation from the last video of what a lower bound is. Like, make sure you go back to the last video if you don't remember the equation for the lower bound. But here's the equation for the lower bound. And okay, again, this is shorthand. Shorthand. If I were to write them all out, it would be actually Z1, Z2, Z3, QZ1, Z2, Z3, and here's this gigantic join, QZ1, Z2, Z3. So they are the same, it's just this is the shorthand. Okay? Now, our goal is to find QZ1, 2, 3 that maximizes the lower bound. Okay? We want to maximize this by picking this. So how do we go about picking it? This is very hard because even the people that invented variational inference had no idea. They didn't know how to solve this either. But they did have an idea that could simplify the problem by making an approximation. So they came up with a good idea. Bing. A good idea. And the idea is that instead of assuming that this distribution could be anything, we restrict it so that it will simplify the math by making some assumptions. So the assumption is this. Well, this is the distribution. Well, maybe we can assume that Z1, Z2, Z3 are independent. If they're independent, it really means that we can separate them. Instead of Q, Z1, Z2, Z3, now we divide it into 3 separate functions. We like separated them, or you could write it like this, where is the product. Okay. And now, well, if we look at it from this way, we can now plug this into the original lower bound equation. So remember, here was the lower bound equation that we were working with. So I'm going to assume that I can separate QZ1, Z2, Z3, and I'm going to assume I can separate that. So I rewrite this whole equation here. Notice how QZ1, 2, 3, QZ1, 2, 3 are separated. Okay, so they're separated, and now we start the mathematical manipulation. Well, first thing I do, I notice that this is the log. Log of x and y is the same as log of x minus log of y. So this is a very good property you should have learned in calculus. And because of this property, notice that I separated the two of them. Now, if log of division is subtraction, see, subtraction. What about log of multiplication? So right now we have log of, if we have log of xyz is equal to log of x plus log of y plus log of z. So similarly here, right? So I'm gonna separate that as well. So actually, let me make sure I write that down. Log of x, y, z is equal to log of x plus log of y plus log of z. So now is instead of x, y, z, we have qz1, qz2, qz3. So because of this negative here, everything will be negative. So I have log of qz1 minus log of qz2 minus log of qz3. So that's what I did here. Now at this point, notice that like QZ1, 2, 3, they're all kind of separated. So maybe we could just solve them one at a time because they seem to be separated. And this is a light bulb moment. Hey, maybe we can just solve them one at a time. Well, instead of looking for the entire QZ, oh, well, I'm just repeating it myself. We can solve them one at a time. Yes, one at a time. What if we just solve for QZ1? Okay. And we assume that we know QZ2, QZ3. This assumption is completely false. Obviously, we don't know QZ2, QZ3. But hey, let's just try and see what happens. Maybe something magical will happen. So I'm going to separate out QZ1. Here's QZ1. Here's another QZ1. And I'm going to keep the rest of them still like together. And the first thing I do is I take this portion and just distribute. I multiply here, and then multiply here. Now, if I do that, I get 3 portions. And because it's so long, I separate them out into 1, 2, and 3. Okay, so I separated them out. Basically, over here is this part. Over here is this part. And over here is this part. Okay. Now, for some of you, I might be going very slow. But because this is a video and you can't ask questions, I want to make sure everybody can follow. If it's too slow, I definitely suggest you should speed it up. Since this is on YouTube, you can run it in twice as fast. Anyways, so this equation, as you can see, suddenly exploded. It exploded in size, so it's a lot bigger now. So maybe we expand them, and now we want to simplify each one of them. So let's look at them one at a time, and we'll start with 3. So that's the one we just did. So here's the equation for 3, like right here. And if we want to separate out QZ1, we can just move it out here. Notice how I move QZ1 here. And the rest of the formula here doesn't have any QZ1. See, we don't have any QZ1. Look at each one of these. Well, since none of them are QZ1, what that means is this right here is known, and therefore it's just some constant. Remember, we assume that if we want to find QZ1, we know QZ2, QZ3. I am aware that we actually don't know, but let's assume that somehow we do know. And therefore, if we do know, we can treat this as a constant. Okay? And what we end up having, that part 3 is this first portion right here, with multiplied by some constant. Again, first portion and some constant. That's part 3. Okay, well, let's look at part 2. Here is part 2. We have the equation here. And again, we want to separate out QZ1. So QZ1 is over here. Oh, sorry. QZ1 is here, and QZ1 is here. So this term and this term can be moved out. Notice how I moved them out here. This goes here. This goes here. That's how I got it. And the rest of them, goes here. Now, if we look at this portion right here, right? If we look at this portion, it's just, this is the probability distribution, and I'm just summing all possibilities. Now, when I do that, the sum of all probabilities are always 1. I mean, obviously, that's like the first rule of probability. So it's always 1. Therefore, this is just gone. That's equal to 1. But the remaining, that becomes part 2. Okay? So part 2 is now equal to this. So we did part 3, we did part 2, and now look at part 1. Okay, so this is the equation for part 1. I copied it down here already. And again, we want to separate out QZ1. There's only one, but there's another QZ1 here. But you can't separate this out because they're all joined into one function. So that's kind of stuck in there. Okay, well, in that case, I guess I can only move QZ1 outside. But what we could do is, now remember the definition of expectation. If we have expectation of x, it's the same as this formula, x times the probability of x, and you sum up all the possibilities. Now, if you have expectation of some function of x, then instead of x here, you have some function of x. Now this form is very important. What we have is there's some PDF function, and there's some function, and you're summing up all of them. So here's the sum. There's the sum portion, some function, some PDF. Does that look familiar? Well, in part 1, this is some probability distribution. This is some function, and this is the sum of all of them. So this is some PDF. This is some function. And here's the sum. Now, if we follow this same expectation rule, we'll get this right here. Expectation with respect to Z2 and Z3 is of this whole thing. Remember, here's the function, and we moved it in here. Okay, so this now is equal to part 3. Sorry, part 1. Part 1. Well, let's put all 3 parts back together. Right? 1, 2, 3. Let's put it all together. And we end up with this function, where the lower bound is equal to part 1 that we calculated, part 2 calculated, and part 3 that we calculated. What we want to do first is we want to put 1 and 3 together. So 1 and 3. And notice that QZ1, this is the same as the QZ1 here. So we can combine the QZ1, and the rest is just the expectation and constant. Expectation minus the constant. That's where I got that from. And here's just part 2. Okay. So now we have this is the lower bound. All we have been doing so far is playing with different manipulations of the lower bound to simplify it by making it more complicated, less complicated. And this is our form of lower bound. For today, I think this is enough derivation. You want to make sure you can get to this point. Our goal, again, we want to remember, our goal is to maximize the lower bound, okay? Maximize this lower bound. And then so far what we've done is we have basically manipulated the math, the algebra. We have manipulated the algebra to create this form. I'm going to end today. In the next video, I am going to continue with basically making the lower bound simpler. Like, as you will see later, that we can essentially take this and simplify it further and further until eventually we can reach a certain conclusion. So, okay, so this is it for today. Thank you for watching. What this is 4? Yeah, part 4. I will see you in part 5.